here there is a steam power plant operating on an ideal regenerative Rankine cycle with one open feed water. So there is only one open feed water heater. So steam enters the turbine at 15 megapascal, right? So it says this is the turbine, right? So this is the turbine. Steam is coming into there with 15 megapascals. So and temperature is 600 Celsius. The steam expands through the turbine and is condensed in the condenser at pressure 10 kilopascal, right? So this is the condenser. The condenser pressure is 10 kilopascal. Then during the expansion, a portion of the steam is extracted from the turbine at pressure 1.2 megapascals, right? So here there is some amount of steam extracted, let's say y. So if we consider 1 kilogram is coming steam, so y kilogram is coming there, and the other is 1 minus 1 y, right? So it is going through the condenser, right? So extracted from the turbine at pressure 1.2 megapascals, right? So the pressure of the extracted steam is 1.2 megapascals, right? So it is directed to the open feed water heater, right? So this is the open feed water heater. The condensate from the condenser is first pumped to the feed water heater 1.2 megapascals using the pump 1. So 1 minus y is pumped into the open feed water again, right? So it is also 1.2 megapascals. So the extracted stream mixes with the feed water, producing a saturated, right? So it says saturated liquid at 1.2 megapascals, right? So actually in here there is steam, right? Here there is actually liquid, right? So to mix properly, all need to have a constant pressure, right? So same pressure actually, right? This is 1.2, 1.2, 1.2. That is the reason. Otherwise they will not mix properly, right? So the mixture is then pumped into the boiler 15 megapascals using pump 2, right? So okay, here it says pump 2, right? The water boiler, then the water enters the boiler where it is heated to become superheated at 15 megapascals, right? Okay. Okay, here the boiler pressure is 15 megapascals, right? That is mentioned there, and boiler temperature is 600 Celsius, right? This is 600 Celsius. Yeah, okay. So here first they are asking mass fraction of the stream extracted at 1.2. The value which I marked here, right? Y. They are asking y. So let's find that one. So firstly we have to do what we have to do is we have to draw the TS diagram, right? So now I am going to draw the TS diagram for this. This is my temperature axis, let's say in Celsius. This is my entropy axis. The units are kilojoule, kilogram, Kelvin. right? So let's draw this one. Okay, so we know the shape of that one. Now I'm going to mark pressure lines, right? So there are actually three pressures: 15, 10 kilopascals and 1.2 megapascals, right? So there are three pressure lines. This is my highest pressure line, which is boiler pressure. This is my second pressure line, and this is my third pressure line. Okay, so let's mark this is 15 megapascals. This is 1.2 megapascals. This is 10 kilopascals, right? Okay. Let's draw the TS. Let's complete the TS diagram, right? So we will start from pump 1, right? So it says it produces saturated liquid, right? So yeah, so generally condenser makes saturated liquid, right? So this is 1, pressure is 10 kilopascals. Okay, so 1 to 2, it goes to 1.2 megapascals, right? So this is my 1.2 megapascals, so it goes like this, 1 to 2. So then 2 to 3, right? So 2 to 3, it is a mixing process, right? So actually there's no change in the pressure, right? So let's say 3, where is the 3? Here pump 2 starts here, right? So and actually it says here it makes saturated liquid, right? So here this is saturated liquid, right? So from 2 to 3, this is saturated liquid. Then 3 to 4, it is again pump, right? So 3 to 4, like this, 4, right? Here it is 4 state. So 4 to 5 is boiler, right? It is continue up to 600 Celsius. Okay, let's say this is 600 point. So this is 600, right? This is actually boiler, right? So 4 to 5, it is 5. Then what happens? 5 to 6, 5 to 6, it is 15 to 1.2 megapascals, right? So okay, so it do some workout. So it is going from 15 megapascals to 1.2 megapascals, right? So from 5 to here, it is 1.2 megapascals, which is stage 6, right? From 6, it extracts some stream Y, so it is going here. This is the extracted Y stream. So here it comes 1 kilogram. There it goes Y kilogram, right? Like that. Then what happens? 7 is in 10 kilopascals, right? So what happens? If it goes further down, here it is 7, right? Actually I don't know it is in here or here, right? So let's figure it out, right? while watching the tables. So this is 7. So it goes from 7 to 1 again, right? Here 7 to 1, it is condenser process. Okay, so it coming 1 kilogram, so it extracts y kilogram, so 1 minus y is going out, right? So this is 1 minus y, this is again 1 minus y, it extracts here 1 minus y, and y mixes here and produce 1 kilogram again, right? So the cycle continues like this. So here to here, 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 like that. Okay, so I hope you guys understood. Okay, so if you guys have any questions, please comment below, right? Okay. Let's continue. Now we have drawn the T diagram. Now we have to find the mass fraction, which is y. Okay, first of all we have to find entropy values and so we have to find enthalpy and entropy in each state, right? So let's start from state 1. Okay, so there we know that pressure, right? It is 10 kilopascals, and it is in saturated, right? So it is saturated, and its pressure is 10 kilopascals, right? So let's go to the tables. Here there is tables, so we need to find 10 kilopascals, which is here. This is 10 kilopascals. We need to find HF. Here there is HF. So here 190.191.81, right? H1 is 191.81 kilojoule per kilogram. So actually we are considering work input is approximately 0, so H2 minus H1 approximately 0, so H2 equals H1 equals 191.81 kilojoule per kilogram. Okay, so state G is again in saturated region, so the pressure of that state is 1.2 megapascals, which is what 1.2 into 10 to the power 3 kilopascals. So this is 1 to 100, right? Kilopascals. Similarly, this is 1500 kilopascals. Okay, so 1200 kilopascals. Let's go to that part. This is 1200 kilopascals. We need to find HF. So 798.33. 798.33. H equals 798.33. This is kilojoule per kilogram. Similarly, H4 equals H3, so H4 equals also this value. Okay, so let's continue. Actually this is in superheated region, right? So let's go to the superheated region and read 15 megapascals and 600 Celsius value. Let's go to 15,000, this is the value. We need HF, right? So HF, okay, this is HF, which is 1610.3, right? H5, right? 1610.3 kilojoule per kilogram. So since this is an isentropic process, we have to find entropy values also, right? So S5 equals sorry, I have made some mistake, right? Here I need to go to the superheated region, right? I just found the value in saturated pressure. So let's go to the superheated region here. So now let's find 15 megapascals. So 15 megapascals. There. This is 15. Need to find 600. So this is H value. This is entropy value. There's a huge difference, right? 3583.1. This is 6.6796. Okay, so we found these values. So now let's find what is H6, right? So for that we are using the isentropy process, right? So we are equaling S5 and S6. Okay, so we know that S5 equals S6 because it is an isentropic process. So now we have to figure out this 6 point is in this region, no, this region, right? So for that, let's consider let's found this value. What is the entropy value at that point? So this is SF, right? So sorry, SG, right? So SG. Okay, so we are finding SG at which pressure value? 1.2 megapascals. 1.2 megapascals, which is equals to okay, let's go to the saturated region. I need SG, right? So SG is here, this going to here, so 6.52, right? 6.52. So this is lesser than S6, right? So entropy value at 6 is greater. So we can determine 6 is in to the right of SG at this value, right? So it is in superheated region, right? So I can say 6 is in superheated region. Okay. Now we found that 6 is in superheated region. So what we can do? We can say so we can simplify what is H6, right? So H6 equals to, now we have to do some interpolating, right? So we know entropy value at that point, right? So we are considering 1.2 megapascals, right? So I know at some point entropy value is 6.6796, right? So at that point I need to find enthalpy value. So let's figure out what is this. So let's go to 1.2 megapascals in superheated region. (1.2) is there such a line? Here, this is 1.2. So now what I'm going to do is find 6s line. So I got 6.67, right? So it is in between here, right? So 6.959, 6.5909 with 2816.1, right? The entropy value at the enthalpy value at that point. So entropy value is 6.831 and enthalpy value is 2935.66, right? So let's write that one. So this is 6.8313 with 2935.6, right? So by interpolating I can find H6, right? So I can find that as, I will show the steps, right? So 2935.6 minus something. Actually we can do that in the calculator, right? Using calculator. We can find H6 equals to 2859 kilojoule per kilogram, right? So we have found that. Now let's go to finding the enthalpy value at 7, right? So I know entropy value of 7 is equals to S6 and S7, right? So all of these values are equals. So S7 equals to this value, 6.677, right? Let's find S gas at which value? 10 kilopascals. Let's go and find that value. Here SG is here, so 8.1488, right? So it is 8.15 or something. So this is actually greater than S7, right? So I can say this value SG, this point is greater than S7, right? So the way I drew the diagram is correct, right? Because 7 is in wet region. So I can say 7 is in wet region. So if that is in the wet region, I can write S7 equals SF plus X SFG, right? So S7 is 6.677, right? 6.677, but 6.6796. equals to we can find SF, right? SF is 0.6492, right? 0.6492 plus x times SFG is what? SFG is 7.4996, right? 7.4996. So by simplifying this, I can find x as 0.8, right? So I have found the x value. So similarly, I can find H7 equals HF plus HFG. So by simplifying this, HF is what? HF is 191 point and HFG is this. So let's substitute there. So 191.81 plus 0.8 times 2392.1. By simplifying this, I can get 2106 kilojoule per kilogram. So I have found H7 also. Okay, so actually I have found every point, right? So now let's go to the determine the mass fraction of the stream, right? Okay, so here let's draw the open feed heater. Here it comes steam at 6 state 6 and liquid at state 2, right? Then it flows out at state 3, right? So here there is y stream, y fraction. Here there is 1 minus fraction. There goes 1 fraction, right? So by using standard SFEE, standard not the standard, steady flow energy equation, right? So steady flow energy equation to the open feed water heater. So sigma E in equals sigma E out, right? So E in is y times H6 plus 1 minus y times H2 equals 1 times H3, right? So I know y times H6 is what? H6 is 2859 plus 1 minus y times H2 is what? H2 and H1 equals, so 191 point what? 81 equals H3. H3 is 798.33, right? 798.33. So by simplifying this, I get y is 0.23, right? So I get this. So answer for the first part is done. So they are asking the thermal efficiency, right? So for that I have to find we know the equation for the efficiency, right? It is work net over Q in, right? So here work net is work out minus work in over Q in, right? So in the Rankine cycle, work in approximately equals to 0. So this becomes work out over Q in, right? by looking at the diagram here, turbine does some work here, right? 5 to 6 and 6 to 7, right? So here 5 to 6 there is 1 kilogram, but from 6 to 7 there is only 1 minus y to do the work, right? Here Q in is from boiler, right? So it is from 4 to 5, which is giving the 1 kilogram, right? So there is no other terms, right? So we can consider Q in as H5 minus H4. There is no change here, H5 minus H4, but in the workout from 5 to 6 it is 1 kilogram, so there is no change there. It is H5 minus H6, right? It is 1 kilogram, but from 6 to 7 there is only 1 minus 6 kilogram, right? So H6 minus H7 there is only 1 minus y, right? So we have to find this value. So H5 is what? H5 where? H5 is 3583, right? This is 3583 minus H6 is 2859, 2859 plus H6 is again 2859 minus H7 is what? H7 is here 2106 times 1 minus 0.23, right? Over H5. It is 3583 minus H4 is what? H4. Here H4 equals H3 equals 798, right? 798. Okay, so this equals to 0.4682, right? So by changing it to by converting it to the percentage, it is 46.82, right? So this is the thermal efficiency of the system. So I hope you guys understood the question, right? So if you guys have any questions, please comment below. Thank you for watching. See you in the next video.